In this video, we will cover the immune system. We're going to be learning about how the immune system has the ability to distinguish between pathogens that need to be eliminated from the body and the body's own cells that need to be protected so that we remain healthy. The content that we are covering, if you would like to look at an additional resource, is covered in Chapter 21 of your OpenStax text. So I've broken this up into two videos. In this first video, we're going to describe the barrier defenses of the body. We're going to show how the innate immune system or immune response is important and how it helps guide and prepare the body for the adaptive immune responses. We'll describe various soluble factors that are part of the innate immune response. We're going to explain the steps of inflammation and how they lead to destruction of a pathogen. And then finally, we'll briefly touch on the advantages of the adaptive immune response over the innate immune response, and we'll also touch on it a little bit in the next video as well, okay? So these other learning goals are just things that we'll touch in the second video, okay? Immunity describes the ability of the body to prevent pathogen entry or destruction of any pathogens that enter the body so that the body remains free of disease. And so, you know, the presence or multiplication of a particular pathogen or bacterium, if it goes unchecked in the body, it may cause an infection or disease, which puts the body in a state where it is homeostatically imbalanced. A pathogen is a disease-causing organism. An antigen is a molecule that marks cells in the body. We typically call this opsonization, and I should have put this term on the screen, but you'll hear it again I'm not sure in this video, but you'll definitely hear it again throughout the semester. But essentially, antigens have the ability to kind of label cells so that the immune system can distinguish self molecules from molecules that do not belong to self. Antigenic sites are specific regions on an antigen that are recognized by the immune system, particularly by antibodies or immune receptors. And so when an immune cell encounters an antigen, it binds to these antigenic sites, triggering an immune response. The diversity of our antigenic sites allows the immune system to recognize a wide variety of pathogens. Why do we need an immune system? Well, the immune system is going to protect us from pathogens and other agents. It's going to protect against cells that are abnormal and grow abnormally, like cancer. Now, the immune system is not a true organ system. It relies on many different structures and organs throughout the body to accomplish its goal. So it's more like a functional system. The immune system is practically going to touch every aspect of the body in some form. And so there are going to be specialized cells in the cardiovascular system. The blood, we have, you know, our white blood cells, which are going to play a huge role with the immune system's response. The lymphatic system and their organs, the skin is going to serve as a barrier. So there are many different organs that are going to contribute to the functional role of the immune system. All right, so the general functions of the immune system include fighting pathogens. Pathogens are going to vary in terms of what they are. So we have microorganisms, which can include bacteria, viruses, fungi, protozoans, parasites, which are larger organisms that are going to include the worms or hookworms or tapeworms. It's going to play a role in removing worn out, damaged, and abnormal cells. So we see this in cases of cancer and some autoimmune disorders. Now, there are two intrinsic defense systems that act both independently and cooperatively to provide immunity and resistance to disease. Immunity is resistance to disease. We have the innate defense system, which is the immune system that we are born with. It provides a very general and non-specific response to pathogens. It has two barricades. We have the first line of defense, which typically consists of our surface barriers like our skin and the mucosa layers that kind of line the entry points to the body. And then we have the second line of defense, which is activated after the first line of defense has been breached. And it typically is going to rely on our antimicrobial or antiviral proteins, phagocytes, and other cells that will work to stop invaders from spreading. And so a popular result of the actions of the innate immune system is going to be inflammation. Now, the adaptive defense system provides the third line of defense, and it takes a little bit longer to initiate because our bodies actually have to develop and mature this part of the immune system. But it has the ability to provide a highly specific attack to recognized invaders. And so here you just see a simplified overview of the innate and adaptive defenses. With the innate defenses, remember they're general and non-specific, so they're going to include our surface barriers, our skin, and our mucosa membranes. And then the second line of defense is going to be those internal defenses. So when we have broken the skin barrier or we have broken through the mucosa layer, then we're going to see the phagocytes come out, the natural killer cells, the inflammation, antimicrobial proteins, etc. Okay. Down below you see the adaptive defenses. That's something that we're going to spend time talking about in the next video, where we have humoral immunity and we cover B cells, and then cellular immunity where we cover our T cells. All right, so innate immunity, innate defenses are non-specific, they are general. They include our mechanical barriers, which are just going to be our skin and mucous membranes, and their main goal is to prevent entrance of pathogens into the body, okay? So this includes the epidermal layer of our skin, hair, the cilia within our respiratory tract. These barriers are considered to be the first line of defense. Anything else that's non-specific in general will be considered to be a second line of defense, okay? So we'll just talk about kind of how these work. The epidermis sloughs off and removes bacteria that may be sitting on the skin, okay? The cilia within the epithelium in the respiratory tract has the ability to kind of trap and sweep away pathogens. Hair can trap pathogens. Tears, saliva, and urine all have the ability to wash away microorganisms. So these all work as a first line of defense to kind of prevent further entry of the pathogen into the body. So when a surface barrier is breached, like in situations where we might have a cut or a nick that kind of goes a little deeper into the skin or into the deeper tissues rather, it's going to trigger the internal second line of defense that protects those deeper tissues. And so the second line of defense is going to include our chemical barriers, our natural killer cells, and our phagocytes. All right, so chemical barriers are going to provide a chemical barrier to pathogens, okay? They include enzymes such as pepsin. Pepsin is in our stomach and our gastric juice, and it can destroy microorganisms, okay? Tears have lysosomes that can destroy microorganisms as well. Defensins are peptides produced by neutrophils, and they can cripple microorganisms by basically poking holes in the walls of their cell membrane and causing them to and lead into their destruction, essentially. And then finally we have collectins, and collectins are proteins that can protect against many bacteria, yeast, and some viruses. Now, we talked about some of those chemical barriers in the previous slide. Oh, it won't let me go back. We're going to talk about a few special proteins, okay? So we have some antiviral proteins called interferons, okay? Infected cells will release these proteins called interferons, which alert the nearby cells to defend themselves by blocking their viral replication, okay? So these special proteins kind of send off an alarm to the neighboring cells to let them know that, hey, I'm infected with the virus. We need to cut off the replication machinery so that we don't continue to spread this virus out the body. And so these antiviral proteins interfere with the proliferation of the viruses and it stimulates phagocytosis and enhances the activity of the cells that help resist the infections. Okay. We also have a complement system, and the complement system consists of some antimicrobial proteins, almost 30. I think there's actually maybe a few more than 30 antimicrobial or complement proteins in the blood. But basically, they can activate and enhance inflammation and kind of bring attention to the area that is damaged or is infected. And there are all ways that it can directly destroy bacteria. It can act very similar to the defenses where they poke holes into the cell wall and causes its collapse. Okay, the complement system, as its name implies, it complements the immune responses, so it can enhance both the innate and adaptive defenses. All right, so the natural killer cells represent a small population of lymphocytes, but to be clear, do not, and I know we haven't really talked about the B and T cells yet, but please do not confuse the natural killer cells, which are a population of lymphocytes, with the B lymphocytes and T lymphocytes. They're in two different kind of categories, okay, and they're two different things. But the natural killer cells can defend against viruses and cancer cells by secreting cytolytic substances called perforins that can go in and kind of lyse and tear that cell membrane. They are not phagocytic. They work by inducing apoptosis, okay? And apoptosis is a natural process that our cells go through to self-destruct, okay, in a controlled way so that the body can remain healthy by removing the damaged and unnecessary cells within the body, okay? They can also secrete cytokines, which can influence and enhance inflammation. All right, so phagocytes have the ability to ingest and digest foreign invaders, and they include our macrophages, our neutrophils, our dendritic cells, our mast cells, and our monocytes, okay? Neutrophils are the most abundant phagocytes, but they are some very hard workers. They die fighting. So whether they are killing ingested or extracellular targets, typically they are also going to destroy themselves in the process. Now, in contrast, we have macrophages, which are a little bit more robust and they can survive to kill another day. They're not going to be as susceptible to self-destruction by their own machinery as the neutrophils are. Macrophages can be fixed, where they remain permanent residents of the organs that they are protecting, or they can be free macrophages, where they have the ability to wander through the tissue spaces. All right, so here is the process of phagocytosis. Initially, what you're going to see is that the phagocytic receptor, let me get my laser out here, is going to bind to the pathogen, okay, as you guys can see here. And so then the phagocyte is going to engulf the pathogen and form the phagosome, okay? The phagosome is going to fuse with a lysosome, so you see this here, and it's going to create the phagolysosome, okay? The lysosome is very important because it has these acidic enzymes that's going to be able to kind of break down the pathogen into very, very small fragments, okay? So the enzyme is going to destroy the pathogens, and then the waste is going to be removed, as you can see here, by exocytosis. In our innate immune system, certain cells are going to have specialized pattern recognition receptors, like our toll-like receptors, as you see in the example on your screen, we call them TLRs, that bind tightly to structures on microbes before they do harm. And so basically these receptors, they recognize specific molecules And these specific molecules, we call them PAMPs. And PAMP stands for pattern associated molecular patterns. And these specific molecules are not present on human cells. And so when they become visible on a cell within the body, it allows the immune system to be able to distinguish between the harmful invaders and our own tissues. Now, when TLRs bind to these pathogen-associated molecular patterns, they trigger a chemical alarm that activates the body's inflammatory response. And so this inflammation helps to contain the infection and recruit other immune cells to fight off the threat. Body temperature is a systemic response to invading microorganisms. Now, some of our lymphocytes and macrophages that are exposed to pathogens will secrete a particular chemical called a pyrogen. And a pyrogen, when it is released, is going to cause an increase in our body temperature. One of the pyrogens that is released by some of our lymphocytes is called interleukin-1. And this pyrogen is going to act directly on the hypothalamus, causing an increase in our body temperature. Now, some of the benefits of having, a moderate fever include the liver and spleen will sequester and kind of take up iron and zinc from the blood, which is important because those nutrients are important for microorganisms. They can utilize those nutrients for their growth and development. It also can increase phagocytic activity, metabolism, and enhance the rate of repair. Inflammation is a non-specific response to tissue injury. It's going to prevent the spread of pathogenic agents to nearby tissues. It's going to get rid of any debris or pathogens in the area. It's going to set off an alarm and alert the adaptive immune system, and it's going to set the stage for repair. We have acute and chronic inflammation, where acute inflammation is the body's immediate short-term response to injury or infection. And typically what you're going to see with the acute inflammation is redness, heat, swelling, and pain, okay? It involves rapid activation of our immune cells and the release of chemicals like cytokines, which are going to help fight off the threat and promote healing. Now, on the other hand, we have chronic inflammation, and that is a long-term persistent response that can last for months or even years. It occurs when the immune system is consistently activated, or it continues to be activated after an event of an ongoing infection. So like, for example, like autoimmune diseases, or just being chronically exposed to irritants. This can lead to tissue damage and contribute to conditions like arthritis, heart disease, and cancer. So how do we know if inflammation is present? Well, inflammation is going to produce 4 cardinal signs, and that includes local redness, swelling, heat, and pain, okay? Tissue injury is going to result in the release of paracrines like histamine and other inflammatory mediators from mast cells. Histamine is going to cause vasodilation, okay? And vasodilation leads to the redness that we see, okay? What happens when the capillaries in smaller blood vessels expand and vasodilate, we have an influx of blood, and so we see the color change due to that, okay? Increased blood flow will cause the production of heat. And so that's also kind of going to be driving, the vasodilation is also not only driving the color change, but also the heat that we see, okay? Pain is going to be due to innervation or stimulation of nearby pain receptors. The inflammatory mediators also improve vascular permeability, which is going to allow for fluid to have an easier time leaking out of the vessels. And because the fluid leaks out, it's going to lead to accumulation of fluid in nearby tissue. So what we would see is swelling that results from increased capillary permeability and fluid entry into those spaces. Okay. On your screen, we have these inflammatory mediators that are going to contribute to the process of inflammation. Histamine is going to be released from mast cells and basophils, and they're going to promote vasodilation and increase permeability. Okay, they're also going to lead to the formation of exudate. And we talked a little bit about how, like, with the vasodilation and increased capillary permeability, the ability for fluid to easily move out. Well, exudate is a fluid that leaks out of the blood vessels into the tissues during inflammation. We have kinins, which are peptides derived from the plasma protein kininogen. So like, for example, bradykinin is a kinin, and they are also going to contribute to vasodilation and increasing the permeability of those capillaries. This, as a result, is going to induce chemotaxis of leukocytes. So it's just basically marking the areas so that leukocytes know where to go, and inducing pain. Okay. Prostaglandins are fatty acid molecules, and they're going to have the same role as histamine. They're in the kinins. They are going to induce neutrophil chemotaxis, and they're also going to induce pain. Cytokines is just a general term that describes chemical messengers that can influence cellular development, cellular differentiation, and responses from the immune system. They are going to include our interferons and our interleukins, and some of our growth and suppression factors. They allow cells the ability to be able to communicate with each other over short distances. All right, I told you we would have another conversation about the complement system, and here it is. All right, so the complement system, as you remember, it consists of proteins. Okay, we call them our antimicrobial proteins, that are going to be found in blood and tissues, which are normally going to be inactive but can be quickly activated if a pathogen enters into the body. Now, once activated, these proteins work together in a cascade of reactions to perform several different functions. First, they're going to help kind of mark and opsonize the pathogen for destruction through a process called opsonization, where they bind to the surface of the pathogens and make them easier for our immune cells to be able to recognize them so that they can take them down, basically. Secondly, they can directly destroy pathogens by creating holes in the plasma membrane, causing it to break apart. Additionally, our complement proteins are going to promote inflammation by attracting immune cells and playing a role with that chemotaxis to the infection site, enhancing the immune response in that area. Most importantly, the complement system is tightly regulated to prevent damage to the body's own cells. And so if this system is activated too much or activated incorrectly, it can contribute to diseases like autoimmune disorders. And so here you can see an example of a complement protein poking holes into the bacterium. And so basically what's happening is that we have a lot of fluids and salts that are allowed to enter and cause an abnormal expansion of that cell. And basically the bacterial cell will expand until it bursts. And that's how it is able to kind of help the immune system get rid of those pathogenic cells. All right, so this image here, it summarizes, and I do want you guys to take a moment to kind of look over it and study it and really understand what it is trying to portray, but it basically summarizes the events that leads to those four cardinal signs of inflammation. We didn't really talk about it, but sometimes there is a fifth cardinal sign, When there's a situation where we have loss of function, we call that the fifth cardinal sign. Also, I want you to note how the pro-inflammatory mediators and their effects can lead to some of the internal responses to injury by the body. Okay, so you have these mediators and how some of the changes that occur can lead to some of those deeper processes that occur in response to injury. All right, so here are your practice questions for this video. Take a moment to review the information that we have talked about thus far. If you have any questions about anything, please let me know.